In this lesson, we will define mass, and explain how mass and weight differ. Mass is a measure of the amount of matter that an object contains. For example, one atom of helium is composed of 2 protons and 2 neutrons. So we can say that a single atom of helium has a total atomic mass unit of 4. The mass of an object is the same throughout the universe. So if one atom of helium has an atomic mass unit of 4, on Earth, it will have the same atomic mass unit on the planet Saturn. In everyday life, we normally deal with the mass of objects that contain many thousands or even millions of atoms, not just one. For these objects, we use the metric units called grams and kilograms. There are 1,000 grams in 1 kilogram, so for small masses we use grams and for larger masses, kilograms. Weight is different than mass. Weight is a force. The weight of an object is equal to the force of gravity between the object and the planet. The force of gravity is an acceleration because the speed of a falling object increases each and every second that it falls toward the surface of a planet. In mathematical terms, force, F, is equal to mass, m, times acceleration, a. Thus, the equation is F equals m times a. This equation was first formulated by Isaac Newton, and is known as his famous second law of motion. While the mass of an object is the same throughout the universe, weight changes with changes in gravity. Even here on Earth, the force of gravity changes slightly from the North Pole, where it is highest, to its lowest value at the equator. As a result, your weight at the North Pole will be slightly higher than at the equator. For example, if you weigh 100 pounds at the North Pole, your weight at the equator will be 99.6 pounds.
Now, let us examine the connection between mass and weight. The metric unit of weight is the Newton, which is designated by the letter N. The weight of an object in newtons is equal to the mass of an object in kilograms, multiplied by the force of gravity. On the Earth, the force of gravity is 9.8 meters per second, each and every second, or 9.8 meters per second squared. Thus, the equation is weight in newtons, equals 9.8 times the mass in kilograms. This is the connection between mass and weight here on Earth. Now, let us look at the mathematical connection between mass and weight. There are 9.8 newtons per kilogram. If we use grams instead of kilograms, there are 0.0098 newtons per gram. Therefore, the weight in newtons is equal to 0.0098 times the mass in grams. Put another way, we can say that 1 newton is equal to 102 grams here on Earth. Now let us look at how weight changes for the same object on different planets in our solar system. If your weight on Earth is 150 pounds, your weight on the planet Mercury will be just 56 pounds. This is because Mercury has only about 1/3 of Earth's force of gravity. However, on Jupiter, which has a force of gravity about 2.5 times that of Earth, your weight would be an astounding 398 pounds. This table shows the force of gravity in newtons per kilogram, for 10 major bodies in our solar system. As a simple exercise, calculate your weight on a different planet. First, measure your weight in pounds here on Earth. Now convert your weight in pounds to kilograms. 1 pound equals 0.454 kilogram. Use the gravity value of a planet you select from the list shown on the previous page to calculate your weight in newtons, then convert to pounds. 1 pound equals 4.45 newtons. If you weigh 100 pounds on Earth, calculate how much you weigh on the Moon. This presentation was produced as a public service to help middle school and high school science teachers develop experiments, presentations, and demonstrations that can be used in their classes. More science experiments and demonstrations are available on the Tops of Santa Clara Valley website at www.topsofscv.org. Teaching Opportunities for Partners in Science, also known as TOPS, is a program aimed at stimulating greater interest in science by middle school students.